Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the most awesome, stupendous stuff. This is the AAS Journal Author Series. And I am very happy to have Yeon Joo Lee with us today. Hey, Yeon Joo.
Yeah, hello. Nice to meet you.
It's a
Thanks
pleasure
for
to
the
meet
invitation.
you are so welcome.
Yeah.
It's a very awesome article that we'll get to. So very cool. Yeon Joo, where are you located at?
Yeah, I'm living in Daejeon. It's a small city. Not small city. It's a city with 1 billion people in Korea.
Goodness. Wow. Oh, in Korea. Very nice. So we're way around the world. So I'm in Phoenix, and we are definitely in our autumn weather. So we have turned the corner. Winter's around the corner. And how are things in Korea?
Yeah, it's also in autumn. I can see some autumn colors outside.
I will look. I will take a look. I see them. I really do.
That's great.
That's an awesome background you have. I like that a lot.
Oh yeah, thanks. It's some graphic of many planets, and I
Yeah,
like it too.
very nice. Did you make that?
Oh no, I downloaded it.
Uh-huh.
I love the drawings, so I'm using it as my background.
Very cool. Very nice. And speaking of very awesome planets and backgrounds, and Yeon Joo, what do you like to do for research?
Wow, yeah, that's a very nice question, and I'm doing Venus research, and I've been doing it for a long time, and quite a long time. It has been 14 years.
A long time.
Yeah. Yeah, and it's really my favorite topic. As a researcher, I love it to do it.
Very
Yeah.
cool. Very cool. And that is going to bring us to this very awesome Planetary Science Journal article. It's open access, so you can go grab a copy for free, people. Go get it. And we have the reflectivity of Venus's Dayside disk during the 2020 observational campaign, outcomes and future perspectives. And Yeon Joo, take us away.
Yeah, thank you. So this article is about the Venus Dayside faraway observation campaign that was conducted in 2020. It was a really big team effort. As you can see, that the list of the co-authors are quite a lot, because we made coordinated observation with 3 spacecraft and 6 ground-based telescopes.
Oh, wow. Okay.
Yeah, it was a really great team effort. And I really appreciate all of my co-authors for their all support and work, what they've done.
Quite the international effort here.
Yeah, that's right. So many European, Japanese, and some American colleagues worked together.
Cool.
And also Turkish and the Korean colleagues too.
Turkey, yep. Very nice.
Yeah, and so if you go down, there is a abstract. And since I'm going to introduce about the contents of this work, maybe I can skip to the introduction.
Sure.
Yeah, so this campaign was very, very interesting, especially for Venus community, because it was targeting 2 goals. The first goal was about the unknown observer, that exists inside of the cloud. And there are many candidates, but it's not so clear what is the source of these observing materials. It has very broad observation features from near UV to all the way to UV part.
Okay.
Cool. Yeah. So there were many efforts to understand what is the nature of this unknown observer, but it's not so easy so far. So we wanted to understand this unknown observer. That was the first goal. And the second goal was that how about the SO2 gas abundance near the cloud top level. Okay. And yeah, its absorption band is also in UV. So in this campaign, we try to understand this unknown observer and the SO2 gas abundance all together using very broad range of wavelengths from UV to all the way to near infrared.
I'm with you. Very good.
Yeah. So if we go to the observation part, yeah, okay. So it's the list of the facilities that participated into this campaign.
Wow.
And the table 1 actually summarized all the campaign places.
Okay.
Yeah, thank you. So the location of the places and also the name of the facilities, which type of the observations, spectral range, date of observations, all summarized in this table.
Nice.
Yeah, so as you can see, 3 spacecraft and the 6 ground-based telescopes were used in this campaign. And sorry that we have to go back. That the figure 1 shows the geometry of this campaign.
Let me get this.
So yeah, that's perfect size. So the upper figure shows that the somehow the viewing locations of 3 locations, 3 facilities. So this campaign actually used a very, very good opportunity of Venus far-away observation by Bepi-Colombo. Yeah, Bepi-Colombo is ESA and JAXA's Mercury orbiter. Okay. And it is in the cruise phase right now. Yeah, it will arrive in Mercury only in 2025.
Oh, good. Okay.
Yeah, but during the cruise phase, okay, in the figure that the Bepi-Colombo is shown, that the trajectory of the Bepi-Colombo is shown as a gray line. So yeah, here, and in 2020, the Bepi-Colombo was able to observe Venus from far distance. So this figure is it's not usual frame, so it's a somehow fixed frame that the Venus is in the lower left side, and the direction of the sun is fixed as the right direction. Right. Yeah, and the Bepi-Colombo was approaching to Venus, and he was able to make Venus observations from the distance of 0.3 AU.
Nice. Okay.
Yeah, and using that moment, that opportunity, we organized all observations at the Akatsuki, which is the currently only one active Venus orbiter by JAXA. Yes. It was operating around Venus, that was located between Venus and the Sun. And the trajectory of the Akatsuki is shown in this, the black curve, there, where you put your mouse cursor. So in the meantime, from the Earth, was able to take Venus data at the same time together. So the viewing geometry of all of these 3 locations are shown in the lower panel. Leftmost is the one Venus as seen from Bepi-Colombo. Middle is that from Akatsuki. And the right one is from the Earth.
Good. Yes.
Yeah, right. So all of these 3 locations were possible to take Venus Dayside observations, to take the Venus Dayside data. And we could cover long range of wavelengths, as I said before. So from UV, so from spacecraft, we could take UV data sets. Right. Yeah. And from the ground, we could take from near UV to near infrared.
Oh, nice. So you got the whole range.
Yeah. Right. Such an opportunity is not so common chance. So we tried all our best. So if we go to the next figure.
Sure. Figure 2 looks like disk integrated albedos.
Yeah, so it shows the Venus image data sets of the Akatsuki Venus orbiter, and also ground-based U-band image data sets. So the observations were done simultaneously from all of 3 locations. And this figure shows that how was then the situation at UV range. Yeah, from these two locations, from the ground and Akatsuki. And the Akatsuki's data sets, since it's an orbiter and it's operating all the time, every 2 hours it acquires UV images.
Okay.
So it has a lot of the number of the data points here. So disk integrated albedo is shown as a function of solar phase angle.
Yes.
Yeah. And Akatsuki's 365 data points are shown with the colored circles with black boundaries.
Yes.
Yeah, these are the Akatsuki data sets near the time of the campaign. Yeah, thanks for the crossing up.
Yeah.
That's nice.
Good.
Yeah, and at the same time, ground-based U-band datasets, which is shown with the diamond symbols. Orange diamond symbols are the ground-based U-band datasets are shown together. Yes. So the same color means at the same time.
Yes.
Here.
Okay. Very important.
Yeah. So this is a kind of some example of how we acquire datasets at these wavelengths, and the lower panel is in the same way that the Akatsuki's dataset but at 2A3 nanometer.
Okay.
So it's nearby wavelengths, but slightly different. But the 2A3 nanometer is important because it's in the center of the SO2 band.
Okay. Yep.
And the 365 is important because it's at the maximum absorption of the unknown observer.
Okay. Got it.
Yeah.
I'm with you.
But all the facilities worked fine, but there was a problem actually. Okay, so in the one of the subchapter is describing about the Bepi-Columbus dataset. Sorry, I forgot what was the number of the subsection, but
we are in, what are we in? We're in 3.1.
3.1 should be about the Akatsuki.
Right, and 3.2 is about Bepi-Colombo.
That's right. So 3.2 is about Bepi-Columbus observations. And the Bepi-Columbus, Bepi-Colombo took Venus data, was really excellent. It was a really important data set, and it was a team effort of the Bepi-Colombo team too. And but the data set couldn't satisfy the quality that we can use it for scientific analysis.
Okay.
Yeah, you know that it was cruise phase, and the Bepi-Colombo's scientific target is Mercury. So Venus was more like a test run of the instrument.
Okay.
Yeah. Yeah. So it was kind of some extra data set, and we, after intensive data quality examinations, we decided, okay, maybe it's not so good to include in the scientific analysis. But the good thing was that we could figure out that what we need for future observation opportunity. That was a very important thing, I think. So even though we couldn't use the Bepi-Colombo data set for this study, but in future campaign, we expect we will be able to use it.
Nice.
Yeah. So yeah. So the campaign data set explanation is continuing in the subsection 3.3 and 3.4. Describing about the other ground-based data sets.
Yes.
Like a Carl telescopes. CCD camera was used, and the stellar telescopes imager also used for this campaign data analysis. And the subsection 3.5.
There's our U-band, this 3.5. There we go.
Yeah, it's another Carl telescope. It was at the PIMAS imaging spectrometer. So this data set provides spectrum
Okay.
information.
Okay.
Yeah. So
Mm-hmm.
the overall comparison and the evaluation of each of the data sets are described in each figures here.
Okay.
So like a figure, I think it's figure 3. Yeah.
Mm-hmm.
Figure 3 shows how was the Venus brightness during the campaign time as seen from Carlisle to observatory that using the CCD camera, we took Venus data at B, V, B, V, R, I. So it's shown in this plot. So at from the ground-based measurement, the Venus's solar phase angle was around 80 degrees. So that's the reason that all the ground-based data sets are concentrated around 80 degrees here, red spots.
Figure 1, yes.
That's right. Yeah, so Malama et al. That the previous phase curve is compared together, and we could see it. Oh, yeah, it's very consistent each other.
Yes,
and
Malama.
Yeah, so the right side shows somehow, magnifying those data sets during the campaign period. Yeah, so the next figure, figure 4, it's again, it's a U-band, but the U-band Venus data sets, but it's shown as in terms of the magnitude. And during after this campaign, actually we realized that in our knowledge, our U-band Venus imaging actually was the first time after Irving and Knuckles et al. Knuckles et al.'s work actually. Wow. There was a long break. And, and our data set was somehow the first one after these 2 previous studies, which is are shown as the blue color curve and the green color curve.
Right.
The Malama et al.'s this data curve is shown with this red line. Yes. This one is a kind of some estimation, so it was not based on the real observations.
Good. Okay.
Yeah, it shows in the ground-based data sets acquired from Stellar telescope, shown in these diamond symbols, and it shows somehow fluctuations. You may see it's not in a line. It shows somehow up and down small fluctuations. Yeah, and that part it looks like a real signal, and I'm going to explain more about it in the later figures.
Okay.
Yeah, so we can move on to the maybe figure 5.
And we got a hexagon.
It's
the big one. Okay.
Right. Right. Okay. So it's our somehow example data sets that was processed within. Okay. It was taken by the PIMAS imaging spectrometer. Okay. So first figure, the A panel, sub-panel figure shows the field overview of this instrument. Yes. So hexagonal shape, the entire hexagonal shape is the field overview, and the individual fibers is shown as somehow in the circles. Yeah, so in the center, there is a few bright fibers that shows where Venus is located. Yeah, that's correct. Yeah, that's correct place. And using those Venus flux fibers, we could extract Venus spectral data set. And the right sub panel shows the how is it the Venus flux as function of wavelengths here. Yes. Yeah, so using those data sets, the spectral data and the imaging data, we could construct somehow the overall data sets in that is shown in the result section. Okay. So we can move on. So maybe it's somehow it's part to explain how is our data sets here. And we use the solar irradiance data sets to calculate the reflectivities.
Okay.
Yeah, and to analyze, to understand our data set, we also did radiative transfer modeling.
Okay.
So the section 4, it's here in this section we described what kind of the things has been included in our model consideration.
Okay.
So yeah, we took into account all of known atmospheric gases.
Yeah.
Okay, so one was a bit problematic because that the somehow old paper mentions about the possible methane gas near the cloud.
Oh.
Yeah, inside of the cloud, inside of Venus atmosphere.
Here, Hodges.
But for this study, we didn't took into account. But the reason I will show you in the appendix contents.
Okay.
So anyway, that we took into account those atmospheric gases, and the details of the atmospheric gaseous database is described in the big table. I think it's in the next page.
So yes, gaseous.
Yeah, here. Yeah, here. So we took the most recent laboratory measurement data sets to take into account those individual gases.
Okay.
Yeah, so people can check the origin of those data sets from the reference.
Yeah, it's very nice to put the references right there on the table. Very nice. Okay.
Yeah, thanks. And if we go back to the previous page, and here in the section 4.2, where we describe about how about in the clouds. Yeah, we should take into account the cloud because it's quite important factor in the Venus atmosphere.
Oh yeah.
Yeah, so we assumed very fine particle, very fine cloud aerosols, which is called as mode 1.
Yes.
And a bit bigger particles, which is called as mode 2 particles.
Yes.
So yeah, so these two particles included as model configuration, and we took into account. We used the quite common assumption that which is that those particles is sulfuric acid aerosols, 75% sulfuric aerosols, and but the problem was that this unknown observer, how we can take into account this unknown observer inside of the cloud.
Yes.
So there are many ways actually, because we do not know what it is, whether it's a gas phase or the aerosol phase. We do not know.
Yes.
So what we tried was that reducing the single scattering albedo of aerosol particles.
Okay.
So that's also described in detail how we handled this part. Yeah, in this page. And yeah, so the figure here that you're showing right now is summarizing about the gaseous observations that has been included in our model. So the A shows the absorption cross sections as a function of wavelengths. And the
detail.
yeah, and the sub panel B shows the extinction coefficient of all of those gases at 70 kilometer altitude, which is the cloud top level of Venus.
Yes.
And the subset, yeah, and the sub panel B shows the assumed abundance of all the gases in our model.
Okay.
Yeah, so this has been used to show the sub panel B here. And the next figure.
Figure 7.
Yeah, Yeah, this part shows the spectral properties of the cloud aerosols that took into account that has been included in our model configuration, like extinction cross section as functional wavelengths.
Okay.
Yeah, or asymmetry vector as a functional wavelengths, and expected that the cloud type altitude as a functional wavelengths.
Ooh, right.
Yeah, so
pretty flat. What is G here? What is G and B?
Asymmetry vector.
Okay.
So that how the scattering are distributed as a function of phase angle that it can provide somehow such a approximation.
Yes. Okay.
Yeah, and the next figure.
Wow, pretty big difference.
Yeah. Oh yeah.
Very big. Okay.
Now it shows that somehow comparisons of our data sets, observational data sets here during the time of campaign. So from the title is shown here from 15th August to 14th September.
Yes.
During the time, the ground-based measurement, as shown on the right side, the y-axis shows the individual observational site, the facilities like a Carlisle 260 cameras, stellar U-band imaging, Akatsuki's 2-band are shown all together as a function of time, as shown in this x-axis.
Yes.
And and it shows quite drastic short-term variations at 283 nanometer and 365 nanometer.
Yes.
Yeah, and that's real variations. The Venus brightness at UV changes a lot because the unknown observer and the SO2 gas, that the unknown observer is very active at the 365 nanometer.
Okay.
And the SO2 gas also changes a lot and affecting 283 nanometer brightness. Yeah, so it's a real signal, and we could see such a temporal variations at U band as well. That the U stellar change. Yeah, it shows also considerable. Yeah, it shows that the fluctuations, and we think it's associated with the real Venus signals, but there is a slight time lag.
Okay.
Yeah, between this U-band fluctuation and Akatsuki's 365 brightness.
Here's a peak. Yes.
Yeah, and we think it's because slightly different viewing geometry. Yeah, it was shown in the figure 1 in the lower panel.
Yeah, let's go back and remind ourselves what that was.
Yeah.
Yes. Here's your subpoint, subsolar, sub-Earth. Yes.
Yeah. So the viewing geometry is not completely the same. So there is somehow it can cause somehow different time lag.
Particularly covered. Yes. Okay. I'm with you. 6, 7. We covered that. This one. Where we're at. Okay.
Yeah. Thank you. So, and we do not see much difference, much temporal variations at longer wavelengths. That was expected because there is no special strong observations except B band, but it's not so significant compared to U band.
Oh, right. Certainly. Yeah, it starts getting wild as you get shorter. Okay.
Yeah, so in the figure 9.
Okay, figure 9. We got some comparisons here. Let's take a look.
Yeah, it's a quite important figure actually. Yeah. So yeah, it's really summarizing all of our campaign observations and model calculations here. We compare everything. So the symbols and the like a circle, triangle, and the square symbol and the blue color lines are all observations during the campaign dataset.
Mm-hmm.
And we show it as a reflectivity quantity as a function of wavelengths in this plot.
Yes. Yes.
Yeah. And the model calculations shown as two lines.
Mm-hmm.
And these two lines are slightly different because of the slightly different cloud top altitude here. And so one used to 70 kilometer altitude cloud top level, and the other used to 64 kilometer cloud top level.
Got it.
The here in the model, it shows pretty good fitting at the longer wavelengths, longer than the 500 nanometer. But there is a significant difference between the model and the observations. It's because in this model, we didn't include the unknown observer in this simulation part. That was what we wanted to retrieve using these observations.
Yes.
So using the difference between the model without the unknown observer and the real observations, which is very clearly shown with this blue curve.
Yes.
We could extract the contribution caused by the unknown observer.
Yes.
Yeah, this part is shown in the result figure. I think figure maybe 13, 12. It shows that the result.
12.
Yeah, 12 here.
12 optical left.
Yeah, okay. So to retrieve the unknown observer's observation spectra,
yes.
Again, we reduced single scattering albedo of aerosol, cloud aerosol particles. So single scattering albedo means that the ratio of absorption compared to the scattering efficiencies. And to explain the difference between the model without the unknown observer and the actual observations, we could try to reduce this single scattering albedo and then could find which value with how much absorption is required to fit the observation.
I'm with you.
And so we could calculate these properties as a function of wavelengths, and our result is shown with this black curve here.
Yeah.
So as a function of wavelengths, and we made somehow normalized, so it's a relative value.
Yeah.
Yeah, and yeah, so black is our result, and we compared our result with previous studies, like Perez Hojos et al. They analyzed the messenger Venus flyby data sets to understand the unknown observer. And actually, we were quite happy that we could see somehow consistent wavelength dependence. Especially that the slope change around 410 nanometer.
Yeah.
In the black line, the slope is slightly different compared to the shorter part, the longer part. And such property was shown in the Perez Hojos et al. It's a blue dashed line curve.
Okay. Yes.
Yeah. And this seems quite interesting because we used entire Venus Dayside disk, and it was the Perez Hojos et al. They used to somehow equatorial region data sets. And since it's consistent each other, maybe there were no special temporal changes between the messenger Venus flyby time and our campaign time. And another important thing from this figure we can find is that the wavelength dependence of the unknown observer's observation seems a bit different from those data sets used in model calculations, which are shown with this, how can I say, this lime color and the orange color lines. So previous model calculations that has been used for the solar heating rate using the unknown observer are shown with these two colored lines. And this unknown observer is quite important factor to understand solar heating rate at the cloud top level, because it's observing solar irradiance in the visible wavelengths in the blue color part. And it can cause very effective solar heating. And our data set and the Paris Hozos data set shows that it seems the visible range absorption might be overestimated in the previous solar heating rate calculations. So it gives us somehow hint that maybe in future studies we can update the contribution by the unknown observer for the heating rate calculations.
Yes, I'm with you.
Yeah, right. So that's the major result of this campaign.
So one question on this: did you end up having so you had two different modes for the unknown observer or unknown absorber? You got me saying it. Did you end up having a preference for the smaller ones or the bigger ones?
No, we couldn't make any conclusion from about the particle size. I think that it needs more study.
Okay. Oh, great. That's a good thing.
That's a really nice question.
Yeah. Okay. Very cool. Very cool.
Yeah. So yeah, in the appendix, it's just like a bonus.
Bonus.
I mentioned about.
Oh yeah, CH4.
Yeah, the methane. And this figure shows that why we excluded methane in our model calculations, really. So if we include methane as reported, the large quantity as reported in one of the previous paper, then its spectral signal is supposed to be really clear, as shown in this red color. Yeah.
Yep.
And such a spectral data clue hasn't been observed really from remote sensing. So that's the reason we so far excluded. Maybe in future, we may have more clues how we can include methane gases.
Cool. Very cool.
Yeah, that is the major part of our
very awesome
campaign.
I'll say it. Very
awesome. Thank you so much.
Yeah, Yeon Joo, thank you so much for walking us through your very lovely article. And you kind of touched on it a little bit there, several times on the future. And so let me ask you, where do you think we go over the next 2 to 5 years on this topic? Or is there going to be other fortuitous alignments between spacecraft, Earth, Venus, and Sun to do sort of a similar kind of project, but a second time around, a little wiser? Are there other telescopes? Is there additional theoretical calculations to be done? Is there laboratory astrophysics to be done on the absorption properties of these gases? And just sort of where do we go over the next couple of years?
Well, yeah, you just said the really exciting part. I mean,
pretty much here, but
yeah. So as I said, that the Bepi-Columbus data set will be okay. So Bepi-Columbus team will try again. With a better strategy. Yes. So we are planning to make a future campaign again.
Cool.
Yeah, it'll be great with more telescopes. Yeah, definitely. Yeah, and I'm pretty sure that there are many people are trying to understand the unknown observer right now.
Yes.
Yeah, so I'm expecting there should be many more laboratory data sets in the coming years, and perhaps we can try to compare more candidates.
What is it? Very cool.
Yeah.
Well, I really look forward to seeing this develop over the next couple of years. Very nice.
Yeah, thank you. Yeah, I'm also looking forward to the next campaign. Yeah.
Maybe we'll do a second article at that point. That'll be great. All right, everyone. Thank you very much. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye-bye.